Okay, now that we've looked at integration in Chapter 5, in Chapter 6 we're going to look at some applications of integration. Kind of just some of the main applications that we'll focus on is we'll continue to talk about area, but we'll also look at the volume of a 3D object, and then we'll do some physics-related problems in Section 6.4. Now there's another chapter, Chapter 8 is another chapter on integration applications, but there is more to know with integration techniques, which is in Chapter 7, and you guys will learn about that in Calc 2. 6.1 is all about area between two curves. Consider this example here. So suppose that we have the curves y equal x squared plus 1 and y equal x. And I want to find the area between these two curves between 0 and 1. Well, of course, the integral notation is notation that we can use to represent area. So if I calculate the integral going from 0 to 1 of x squared plus 1, I'll be finding the area below this parabola above the x-axis and between 0 and 1. Now I don't want that entire region. I want to remove the unwanted space, which would be the area that is below y equal x, if x is going from 0 to 1. Okay? And by removing that little triangular piece there, I'll have what's left over, which would be the area between these two curves. That's what's shaded there in the picture. Okay, I can get my antiderivatives here. It's going to be 1/3 x cubed plus x, being evaluated from 0 to 1, minus x squared over 2, also being evaluated from 0 to 1. When you plug in 1, you get 1/3 plus 1, and then minus 0 when you plug in 0. Plug in 1 here, it's going to be a minus 1/2 plus 0, right? 1/3 plus 1 minus 1/2 is 5/6. Okay, now in general, we will integrate the top curve minus the bottom curve when we want to find the area between two curves for a bounded region. That's what I was doing here. I took the top curve minus the bottom curve. And so in general, that's what you're going to want. And you can represent that as a single integral then. Okay. Here's some notation that you'll see in the book. So y sub t represents the top curve, y sub b represents the bottom curve. Now y is an expression of x. So everything about this integral will be in terms of x, even though I've got y. It's, y is an expression involving x. Okay, in the next couple of problems, I want us to sketch the region enclosed by the given curves and then find its area. That's what you guys will be doing in this section. So here's an example. Suppose that we have the curves y equal 2 minus x squared and y equal x. So I've found where those curves are going to intersect each other by setting the equations equal and then solving for x. -2, -2, and 1, 1 would be intersection points for these two curves. And so I've shaded that enclosed region. That's the region that I'd like to find the area for. Well, everything about my integral is going to be in terms of x. X is going from -2 to 1 in this enclosed region, so that'll be my bounds here. And then I want the top curve minus the bottom curve. The top curve is the parabola, the bottom curve is the line y equal x. Of course, make sure that you got your variable of integration, dx, at the end. And we can get the antiderivative next. It's going to be 2x minus 1/3 x cubed minus 1/2 x squared. We're evaluating this from -2 to 1. Plug in the bounds. When you plug in 1, it's going to be 2 minus 1/3 minus 1/2, and then minus. When you plug in -2, you're going to have -4 plus 8/3, and then minus 4 over 2 is 2. Simplifying that, I'm getting 9/2 as the area of the shaded region that you see. Now I drew a picture geometrically. Here's what's going on. So we have two regions, and the bounds are -2 to 1. Okay, and so of course I could split this into like two integrals. If I didn't do that, but I could have. Now the integral going from -2 to 1 of 2 minus x squared would represent this region here. And you're removing the unwanted space. Okay, So you can see that by removing this little triangular piece on the right, then we'll have what we see on the right here, this enclosed region to the right of the y-axis. Now, of course, any part of the curve that is below the x-axis means that you'll have a negative value. So this little sliver here is a negative. Subtracting another negative means that I'm going to add, if I add this little sliver here, then those two regions are going to offset and basically go away. You won't see that little sliver there anymore. And then now this space, you're going to subtract a negative, means that you'll be adding what we see here to complete the rest of the enclosed region. Okay. Now, as a note, whenever you calculate the area between two curves, you will always get a positive number. We know area can't be negative, and every problem in this section is going to be area related. So keep that in mind. If you ever get a negative, something went wrong in the calculation. Okay. Even though part of the curves are, below the x-axis, that's okay. It works out so that you're removing unwanted space, but you're still going to get a positive number when all is said and done. Okay, here's another example. Suppose that we want to find the area between y equals sine x and y equal cosine x if x is between pi over 4 and 5 pi over 4. So I've drawn the sine curve and the cosine curve and marked out, of course, the curves will intersect each other at pi over 4 and 5 pi over 4. I've solved, by setting these equations equal and then solving for x, I also get those values to show that. Now the sine and cosine curves intersect infinitely many times, making bounded regions of equal area. There's going to be infinitely many of them. So we're going to find the area of one of these regions. Well, the bounds on my integral are going to be pi over 4 to 5 pi over 4. And in that interval, the top curve is the sine curve, the bottom curve is the cosine curve. So it's going to be sine x minus cosine x for my integrand. The antiderivative of that would be negative cosine x minus sine x. We're evaluating this from pi over 4 to 5 pi over 4. Plug in the bounds. Cosine of 5 pi over 4. So let's see here. Cosine of pi over 4 would be 1 over root 2. Okay, but if you flip that triangle into quadrant 3, the adjacent side would be a negative. And so cosine of 5 pi over 4 would be negative 1 over root 2. Now you've got a negative in front of that, so that'll make it so that we have 1 over root 2 right here. And then sine of 5 pi over 4, well, the opposite side is also going to be a negative if that triangle is in quadrant 3. So sine of 5 pi over 4 would also be negative 1 over root 2. Okay, I've got 1 over root 2 minus negative 1 over root 2, or that'd be 2 over root 2. And then when I plug in pi over 4, cosine pi over 4 is 1 over root 2. Sine of pi over 4 is also 1 over root 2. Negative 1 over root 2 minus 1 over root 2 would be negative 2 over root 2. Now I've got 2 over root 2 minus negative 2 over root 2 means that I'll have 4 over root 2, or when you rationalize the denominator, which you wouldn't need to do, but if you did, 2 root 2 would be the exact answer that you'd get there. Okay, here's another one. Suppose that we have y equal cosine x and then y equal 1 minus cosine x. And I want to find the area between those curves on the interval 0 to pi. Well, here's y equal cosine x and y equal 1 minus cosine x. Think transformations. The negative means that you're going to flip the cosine curve about the x-axis, and then the plus 1 means that you'll shift it up 1 unit. Okay, so this curve here would be the curve for y equal 1 minus cosine x. Now if I set those expressions equal and then solve for x, cosine x equal 1/2 means that x would be pi over 3 if you're just solving on the interval 0 to pi. Okay, so I've I've got a scale of pi over 3 on the x-axis just because of that value being a solution to that equation there. And now it kind of depends on which side of pi over 3 you're on here in order to determine the top curve and the bottom curve. So in order to get the total area, I want to be adding two integrals together. Okay, the first one, let's look at the area if you're going from 0 to pi over 3. The top curve is cosine x. The bottom curve is 1 minus cosine x. Okay, and so I've got that set up there, top curve minus bottom curve. And then I'm going to add the rest of the enclosed area. That would be going from pi over 3 to pi. Now on that part of the graph, the top curve, it switches. The top curve would be y equal 1 minus cosine x, and the bottom curve is y equal cosine x. If we simplify then, cosine x plus cosine x is 2 cosine x, and I got a minus 1 there. Here's 1 and then minus 2 cosine x. And get the antiderivatives now. You're going to have 2 sine x minus x. You're evaluating that from 0 to pi over 3. And then x minus 2 sine x is being evaluated from pi over 3 to pi. When I plug in the bounds, okay, sine pi over 3 is a root 3 over 2 times 2. The 2's cancel. That'll leave me with root 3 minus pi over 3. Okay, and then when I plug in 0, sine of 0 is 0. I'll be subtracting 0 there. Plus, okay, over here, when I plug in my bounds, plug in pi, you're going to have pi minus sine of pi is 0. Minus, when I plug in pi over 3, I'm going to have pi over 3 minus 2 times sine pi over 3 is root 3 over 2. The 2's are going to cancel. Going to leave me with root 3. And, okay, so root 3 plus root 3 would be 2 root 3. Negative pi over 3 minus pi over 3 is negative 2 pi over 3, but then plus pi would be pi over 3. So that would be the exact area then that is the total area of these shaded regions. Okay, and yeah, so it might happen where you've got an enclosed region, but you'll have to split it at a certain spot, like what you see here, and pretty much kind of set up two integrals because the top curve will change on the interval. Okay, now there's also some problems where you might have a function of y. When you have a function of x, it's always top curve minus bottom curve. When you have a function of y, I've got two curves drawn. Here's f of y and g of y. And suppose y is going from c to d. You're always going to take the right curve minus the left curve. X sub r means the right curve, x sub l means the left curve. Now both of those would be expressions involving y. Everything about the integral would be involving y. Okay, so even though I've got x here, those are expressions involving y. And so let's take a look at some examples of where we're using this setup. Suppose that we want to find the area between these two curves, x equal y squared minus 4y and x equal 2y minus y squared. These two curves would be parabolas, one facing towards the right, one facing towards the left. To find the intersection points, I've set the equations equal and solve for y, and it looks like, okay, here's 0, 0, and negative 3, 3 would be the inflection, the intersection points. And I've also plotted some more points here on each of these curves to have a more accurate picture. Well, let's see. So y, now everything about my integral has to be in terms of y. In this picture, y is ranging from 0 to 3. Okay, so that'd be the bounds on my integral. And the right curve is x equal 2y minus y squared, minus the left curve would be x equal y squared minus 4y. Okay, and then stick a dy at the end. Combine your like terms. And we're ready to get our antiderivative now. Negative 2/3 y cubed plus 3y squared. We're evaluating that from 0 to 3. And when you plug in 3, negative 18 plus 27. When you plug in 0, both those numbers will be 0. Okay, so I'm getting 9. Remember, again, every one of your numbers are going to be positive when you do the calculation. You will never get a negative. Okay. We'll take a look at one more. So suppose that we want to find the area of the enclosed region for the curves x equal e to the y equal 1/2 x plus 1, y equal 1, and y equal negative 1. Okay, so y equal 1 and y equal negative 1, of course, those are horizontal lines. Here's a slanted line, y equal 1/2 x plus 1, has a slope of 1/2 and a y-intercept at 1. You're going to go up 1 and to the right 2, or down 1 to the left 2, same thing. And then x equal e to the y. If you were to take the ln of both sides, that would mean that y is equal to the ln of x. Okay, so y equal to the ln of x is this curve here. And now, again, everything about my integral has to be in terms of y, okay, because I don't have a function of x. The conditions on y for this enclosed region are that y is going from negative 1 to positive 1, and I want the right curve minus the left curve. The right curve is e to the y. The left curve would be this slanted line, y equal 1/2 x plus 1, but be careful because I need everything to be in terms of y. I wouldn't want to write 1/2 x plus 1, okay? I would want to solve this for x. So if I subtract 1 and then multiply by 2, x would be equal to 2y minus 2, and so that's the expression that would be my left curve that I'd want here. Stick a dy at the end, and then we're ready to get the antiderivative. Now, yeah, so be careful about that. There's some of the problems are going to be where you might need to solve an equation for one of the variables first, so that everything is in terms of that one variable, okay? Just as we see here. The antiderivative would be e to the y, and then minus 2y squared over 2, the 2's cancel, and then plus 2y. We're evaluating that from negative 1 to 1. Plug in the bounds. You're going to have e to the first, and then minus 1 plus 2, minus, when you plug in negative 1, you'll have e to the negative 1 minus 1, and then minus 2. So we have e minus 1 over e, and then negative 1 plus 2 is 1. Negative 1 minus 2 is negative 3. 1 minus negative 3 would be 4 at the end. And, okay, if you were to check, this would be a positive number. And, you know, unless you're told otherwise, you know, again, make sure that the answers are in exact form. All right. We're going to include section 6.1 on the test for chapter 5. It'll be chapter 5 and then 6.1. So be sure that you've looked at these problems here on page 434. A lot of calc books actually have area between two curves in, you know, what you already have seen from chapter 5, okay? You know, because you're still talking about area, okay? You know, they put it in the next chapter, that's fine. So to finish things out here, we're going to, we'll talk about volume next. 6.2 and 6.3 are all about volume, and then we'll look at some physics applications in section 6.4.